Hey everybody, welcome back. It is Monday, and I decided today, you guys had your assignment before the spring break, and I thought before we launch into chapter 14, which is also redox chemistry, I thought I would do a review. So today's class is a quick review of most of the key concepts that you guys learned from chapter 13. If you haven't finished the assignment or the quiz yet, this will be helpful as a nice review before you tackle that assignment and quiz that's due today. And then tomorrow, Tuesday, we will be doing the chapter 14 introduction, and I've given you the weekly overview. So if you haven't read that, take a look at that to see what the game plan is for this week and also next week, because we actually finish chapter 14 end of next week. Then we're done Redox Chem, and then we only have one unit left to do. So that's kind of awesome, actually. We're flying along at a good pace, and because we don't have any labs, which is kind of sucky, but without the labs, it saves us a bit of time. So I think at the pace we're going, we will probably finish a little bit early. We'll see how things shake down in May, but it's definitely a possibility. Okay, anyway, quick review for you guys. Here we go. Fasten your seatbelts. So key concepts for redox reactions. So I went through this on day one. All redox reactions must have a transfer of electrons, okay? That is key. If there's no transfer of electrons, it's not a redox reaction. And there are reactions, chemical reactions, that have nothing to do with transfer of electrons. You're going to see those in our next unit, where we look at transfer of protons, and then there's double replacement reactions, which are also not redox. Okay, if it is a redox reaction, you should be able to identify oxidizing agent and reducing agent using Auger and Rayleigh. If you're asked about an overall half reaction, you can use Oil-Rig, or you can use Leo and Gurr to talk about a gain in electrons is reduction, a loss of electrons is oxidation. And when you're going to balance redox reactions, the electrons gained always equal the electrons lost. And that's what you're doing with those two half reactions before you combine them together, is multiplying them to make sure that electrons are equal on both sides to cancel them out. Okay, sound good? All right, moving along. You don't have this in your notes, by the way. I just pulled out a collection of stuff. You can just kind of watch. If you want to pause and try stuff on a scrap sheet of paper, you can. That's up to you. Okay, you will see this question occasionally. Which of the following is a redox reaction? So when you're looking at these, how do you know? The key is oxidation states. That's the quick, fast way to figure it out. If their oxidation state is changing, then it is a redox reaction. So I'm going to do these quick. Oxygen and fluorine would both like to have a negative. They can't. Fluorine is more electronegative, so it gets its desired oxidation state of -1. There's two of them for a total of -2. In this example, and it's a rare one, oxygen is forced to be +2. Fluorine is the only element that is more electronegative than oxygen. It's the only one that forces oxygen to become positive. So oxygen goes from +2 to -2. So we know it's a redox already because it's gone from +2 to -2. Iodide goes from -1 to -1/3. So there's your other half of the redox reaction. Okay, Na plus, Cl minus. Whoa, where did that go? I just lost it. Right there. Cl minus is 1 minus and 1 plus. Over here, it's still 1 plus and 1 minus for the Cl. Magnesium is 2 plus, 2 plus. Fluoride, 1 minus, 1 minus. Okay, this is a double replacement reaction, and double replacement reactions are not redox reactions. There's no gain or loss of electrons. Everything keeps its oxidation state. So when you see those, you can classify it as not a redox reaction. Oxidation state does not change. Okay, so those are a good example. And so are acid-base reactions, which we'll look at in chapter 15, 16. Okay, reduction and oxidation are both processes. They include the half reaction, Gurr and Leo. So you're looking at the entire half reaction and calling it reduction or oxidation. When you are asked to identify the reducing agent or the oxidizing agent, it's an actual chemical that's inside the half reaction. So in this one, let's break this thing apart, and we're going to do it quickly. Sr goes to its ion, Sr2 plus. We need to add electrons, add them to the more positive side. Okay, there's our first half reaction. In our second one, the ClO4 does not change. It's ClO4 minus, ClO4 minus. It's the calcium we're after. Calcium in here is an ion with a 2 plus, and here it's an element of 0. Calcium 2 plus goes to calcium 0. And you add the electrons to the more positive side. Okay, I could add these up and get the net reaction. We know that ClO4 minus is called a spectator ion. And which one is our oxidizing agent? So give me 1 second. Oxidizing agents gain electrons. That's how I figure it out every time. Who's gaining electrons? Calcium 2 plus is gaining 2 electrons. There's our oxidizing agent, which means this entire reaction must be GR, reduction. And that means this is our Rayleigh. There's our reducing agent. How do I know that? Because it's losing electrons and undergoing oxidation. So this half reaction is oxidation. Isn't redox chemistry fun? Yes, it is. Okay, moving on. Balancing redox reaction. So half reaction method. Rip this thing apart. If you want to try it on your own on some scrap sheet of paper, go ahead and do that. Rip it apart into half reactions, balance the half reactions, and then combine them together to get the net reaction. You should be very good at this by now. HNO3 goes to N2O. Okay, balance all atoms other than oxygen and hydrogen first. 2 nitrogens, 1 nitrogen, 2 nitrogen. Okay, 2 nitrogen, 2 nitrogen, 6 oxygen, and 1. So I need 5 waters to get a total of 6 oxygen. 1 and 5 more is 6. Okay, hydrogens. I've got 2 hydrogens, and over here I've got 5 times 2 is 10. So I need 8 hydrogens on the left. 8 hydrogen ions. I'm skipping states here because I'm rushing through these. Okay, so that means I also need to balance charges now. 8 plus, I need 8 minus. Wow. 8 electrons, 8 protons, 2 HNO3s gives N2O and 5 waters. Okay, H2O2 goes to O2. Oxygens are balanced. We just need to balance hydrogens, 2H plus and 2E minus. Okay, we're done. There's our half reactions. This top one is our oxidizing agent gaining electrons, undergoing reduction. This bottom one is our reducing agent losing electrons, undergoing oxidation. We need to balance the electrons before we can add them together. Times the bottom one by 4. So we get 4 of those, 8 and 8. And now we can cancel out the 8 electrons. And interestingly enough, we can cancel out the 8 protons. And that's it. There's no waters to cancel out. So now we add them up. 2 HNO3 plus 4 H2O2 gives N2O plus 5 waters and 4 O2. And I'm just going to skip states to save a little bit of time. Okay, there we go. Hopefully I didn't make any mistakes on that one, Casey. You will let me know if I did. Okay, build a table of relative strengths. Now remember, the trick to these is identify which group is oxidizing agents. Is it the column down the side or the row across the top? Whoever's more positive is going to be your oxidizing agents, and it's the top. So this is how we will look down to determine strongest oxidizing agents. Most reactions is bromine. Br2 has 3. So Br2 is our strongest oxidizing agent. It turns into bromide, 2-headed arrow, 2 bromides, and we'll need 2 electrons to balance our charges. Okay, there we go. I'm going to skip states again just to save time. Second strongest oxidizing agent with 2 reactions is Ag+, goes to Ag, gains 1 electron. Okay, third strongest is iodine with 1 reaction. I2 goes to I-. So we'll need 2 of those to balance the atoms. I2 to 2I-, 2 electrons, and our last one is copper 2 plus. The weakest oxidizing agent, it needs 2 electrons to become copper. Strongest oxidizing agent, weakest oxidizing agent, strongest reducing agent, weakest reducing agent. Okay, there we go. Strongest, strongest, weakest, weakest. Awesome. Okay, option number 2 is, given just a few reactions, build a table of relative strengths based on the spontaneity rule. And remember, that is, if the oxidizing agent is above the reducing agent, it's spontaneous. If the oxidizing agent is below the reducing agent, it is non-spontaneous. Okay, so the trick to doing these is the pattern. We've got one of these is an oxidizing agent, one of them is a reducing agent. You can figure it out. Whichever one is more positive is going to be your oxidizing agent, and that is the cobalt 2 plus. Okay, it spontaneously reacts with indium. Tells us that it's spontaneous. So that means the cobalt 2 plus must be sitting above the indium as a reducing agent. Just do my dashed lines here. We'll have reducing agents, oxidizing agents. Okay, so cobalt 2 plus must sit above indium in order to have a spontaneous reaction. Now I can complete the half reactions. Cobalt 2 plus is going to turn into cobalt. So it's going to do that by gaining 2 electrons. Indium came from indium 3 plus, so there's its oxidizing agent, indium 3 plus, and 3 electrons. It's really messy. Might rewrite it. I'll just leave it. Yeah, I'm going to leave it. Okay. Next one, copper 2 plus reacts spontaneously with cobalt. Okay, so here's cobalt. Where does copper 2 plus have to sit? Below it or above it if it's a spontaneous reaction? Correct, above it. So copper 2 plus must be sitting there to spontaneously react with cobalt. So it's half reaction, it turns into copper. So copper 2 plus gains 2 electrons to become copper. Okay, so we got 3. Last one, copper 2 plus does not react with palladium. Copper 2 plus does not react with palladium. So copper 2 plus is more positive. There's our oxidizing agent. That must be our reducing agent. So here's our oxidizing agent. Does palladium sit above or below the copper if it's a non-spontaneous reaction? Palladium must be above. Uphill, non-spontaneous. So there's our reducing agent. It's oxidizing agent. You could look up its charge. It's palladium 2 plus as its most common charge. So there's our table of relative strengths. Strongest oxidizing agent, strongest reducing agent. Palladium, then copper 2 plus, cobalt 2 plus, indium 3 plus, weakest oxidizing agent. So then I could ask you all kinds of questions. Who would indium 3 plus react with? And you would say, nobody. Who would palladium 2 plus react with? Everybody. Strongest oxidizing agent. What about indium? Who would it react with? Everybody. It's the strongest reducing agent. Okay, moving on. 5-step method. Usually students don't like this one as much as building their own half reactions. But if you don't know the products, you can't build your own half reactions because you don't know what is on the product side to balance the half reactions. So you have to look them up using your table of relative strengths. So here we go. Oxygen gas, I'm listing all entities present, is bubbled through acidic H+. Solution of chromium 2 bromide. Now because it's a solution, it's an ionic solution, we can break it apart, chromium 2 plus and Br minus. And because it's a solution, we can say that there's water. So those are all the entities present. It makes a blue-green pigment. That's interesting. Okay, here's everything that's present. So now you jump to your table of relative strengths and you start searching for strongest oxidizing agents. Chromium 2 plus is an oxidizing agent, so is this, but this one together is a very strong oxidizing agent, and it is the winner. So it's half reaction from your table of relative strengths. I'm just going to look so you can get the value. If you want to see it, it's at positive 1.23 volts. So if you look at the voltage scale, you can find that half reaction. So it goes oxygen gas plus 4H plus, there's our acidic combo, and 4 electrons makes 2 waters. So there's our strongest oxidizing agent, SOA. Okay, strongest reducing agent. So chromium 2 plus is also a reducing agent. So is bromide, and so is water. I forgot water is also an oxidizing agent. It's a really weak one. So when you look them up, you discover the strongest reducing agent of those three is chromium 2 plus. So as a reducing agent, it will lose 1 electron and become chromium 3 plus, aqueous. Okay, and now before we add these together, we have to balance the electrons. 4 gained, 1 lost. So the bottom reaction is times by 4. Okay, so the overall reaction, oxygen gas reacts with 4 acidic ions and 4 Cr2 plus to give 4 Cr3 plus and 2 waters. Hey, Casey, I remembered the waters this time. Okay, and the electrons cancel out. 4 gained and 4 lost. Okay, diagnostic test. What's going on here? So, things you can look for, and I talked about this before. H plus is acidic. So we're using up the protons. It's becoming less acidic as the reaction moves forward. So if it's becoming less acidic, pH is increasing. And chromium 2 turns into chromium 3. So sometimes you can look up metal ions. And yes, in fact, that's what this blue-green is. I don't have a green color here. Blue-green. There we go. Oh, it didn't give it to me. Grr. There it is. Oh, this is just sucky. Okay. So Cr3 plus is a blue-green. So either one of those would be a good diagnostic test for you guys. Okay. Really, that's about it. Okay. There's some other ones that I listed here in the notes. Pop test, splint relights, so pop test for hydrogen, sprint relights for oxygen, pH with H plus, OH minus. Those are the most common ones. Yeah, I'm just going to leave it at that. I've got this big table here that's in your textbook as well. It has all the diagnostic tests, or the common ones, in the back of your textbook as well. Okay, gone through a bunch of those. Okay, hey, we're almost done. I think we've got 2 things left to do. Disproportionation. So remember this one, where one chemical can be both oxidizing agent and reducing agent. And there's a quick way to figure it out, and that is with oxidation states. So O2, what is the oxidation state of O2 minus? Well, each one of them is minus 1/2, because 2 of them add up to a total of minus 1. So that's a very unusual ion, a peroxide. Well, not really, even just a weird ion. Okay, hydrogen peroxide. So remember the exception to the rule, oxygen is always -2 unless it's a peroxide. Per means lower charge. So in peroxide, oxygen is a -1. There's 2 of them for a total of -2, which matches hydrogen, which is +1 for a total of +2. So hydrogen peroxide, oxygen is a -1. And as an element, it's 0. So here's our disproportionation. It's going from -1/2 to -1, which is a gain of electrons. Then it's going from -1/2 to 0, which is a more positive loss of electrons. So we have a gain and a loss. So O2 minus is both oxidizing agent and reducing agent, disproportionation. All right, so we're going to try and balance this one. The trick to disproportionation reactions is to create 2 of the reactants. So chlorine is the only reactant, so it must be undergoing disproportionation. It goes to chloride, and it goes to ClO3 minus. So balancing half reactions is easy. You can stop the video and try this on your own if you'd like. And if not, you can follow me. So 2 chlorides, 2 chlorines, 2 electrons. Okay, 2 chlorine, 6 oxygen, 6 waters to give me my 6 oxygen, 12 hydrogens. Okay, charges are tricky. Everything's 0 on the left. And on the right, we have 2 minus and plus 12 for a total of plus 10. So we add the electrons to the more positive side. 10 electrons gets us to 0. That's a hard one. Lots of students mess up the electrons on that half reaction. Okay, if I want to do the net reaction, I need to balance my electrons. 10 lost, 2 gained, times by 5. So that would give me 10, 5, and 10. Okay, so electrons cancel out. 10 gone, 10 gone. Okay, 6 waters plus 5 and 1 more is 6 chlorines gives 10 chlorides, 2 chlorate, and 12 H plus. And again, I'm skipping states just to save time. So there it is. Lovely. Balanced redox reaction with disproportionation. One chemical acting as both oxidizing agent and reducing agent. If you did oxidation states in here to show it, this is 0. It goes from 0 to minus 1. That's a gain, so it's acting as an oxidizing agent, and it goes from 0 to plus 5, because that's minus 2 for a total of minus 6, plus 5 is minus 1. So reducing agent losing electrons. Okay, oxidation number. So you have this chart already. Remember that oxygen is always minus 2 unless it's a peroxide, then it's minus 1. Hydrogen is always plus 1 unless it's with a metal, and it's minus 1 as a hydride. Elements are always 0. Ions are the same charge. Watch out for things like carbon and nitrogen and phosphorus. Okay, and the multivalent metals can have 2 or more oxidation states. And the last rule, if you have 2 nonmetals, whoever's most electronegative wins. So there's that example. Chloride and iodine would both like to be minus 1, but they can't. Chloride is more electronegative. It gets its minus 1, which is forcing iodine to be plus 3. Oh my gosh, I'm talking fast and just ripping through this. Okay. So I would like you guys to try and assign oxidation states to this one. If you want, you can write it down and try it on your own. It's a doozy, okay? And then come back and see how you did. Okay, so minus 2 for oxygen, plus 1 for hydrogen. 4 of those is minus 8, 2 of those is plus 2. So that means carbon has to add up to plus 6. There are 2 of them, so each one is plus 3. Plus 3 times 2 is plus 6. Plus 2 minus 8, that all adds up to 0. Okay, so carbon goes from plus 3, minus 2, total minus 4, to plus 4. So carbon goes from plus 3 to plus 4. Is that a gain or a loss of electrons? So it's becoming more positive, so that means it is losing negative electrons to become more positive. So that means this molecule is the reducing agent, and it's undergoing oxidation as it loses electrons. Oxidation state becomes more positive. All right, where's our second player, our oxidizing agent? So plus 1, minus 2 for a total of minus 8, plus 1. This guy must be plus 7, because that all adds up to 0. Plus 7. Okay, what's manganese over here? -2 for oxygen, total of -6. This has to be +6. There are 2 of them, which means each one is +3. So it goes from +7 to +3. It's becoming less positive, so it's an oxidizing agent gaining electrons and undergoing reduction. Now, sometimes you'll see a question where they say, how many electrons were gained, how many were lost? So carbon, each individual carbon goes from +3 to +4. So that is a loss of 1 electron. And then they might say, well, what about the whole molecule, H2C2O4? And the whole molecule, because there are 2 carbons, loses 2 electrons per molecule. Hopefully that makes sense. So loses 1 electron per atom, loses 2 electrons per molecule. Okay, let's take a look at our oxidizing agent. So that was the Mn, goes from +7 to +3. So that means it gains 4 electrons per atom. And if we look at the molecules, there's only 1 manganese there, but there's 2 in that one. So that means the molecule with the Mn2 in it, because it has 2 manganese, gained 8 electrons for the whole molecule because of the 2 manganese each gaining 4 per atom. So in that overall reaction, in order to balance it all out, you'd have to have a gain and a loss of 8. That would be your lowest common multiple, I think, in math. That's the term you're looking for. 8 electrons gain and loss. So that's another trick to balancing these that we don't learn is this is the third method of balancing a redox reaction, where you look at the electrons gained and the electrons lost using oxidation states. So this is called balancing by oxidation states. We don't need to do it because we can do this with half reactions just as well. And one good method is better than learning 2 methods not as well. Okay, so we did that already. Now we're jumping on to our last one. Take a breath. Put on your smiley face. Our review is almost done. Okay, redox titrations. So remember, in redox titrations, there are always a strong oxidizing agent that changes color. So we have permanganate ions that go from purple to colorless, but it'll appear pale pink because of that 1 drop of, I don't know why I'm using orange, 1 drop of permanganate mixed in the colorless water will give you a light pink. And option number 2 is the dichromate ions, when acidic, will turn to green. So these are our strong oxidizing agents that change colors in the presence of a reducing agent. And they're really helpful to allow us to find concentrations of reducing agents. So that's what you use redox titrations for. We're going to do one together and then call it a day. Okay, so you're always given a titration chart. The title of the chart gives you lots of information. So in this chart, we are told that we have 10 milliliters of 0.0500 mole per liter iron 2 plus reacting with, there's our dichromate, and it usually says acidic. We'll assume it is, because they only work when they're acidic. Okay, one of these 2 has to be acidic. All right, so that means that's our strongest oxidizing agent, is the Cr2O72 minus. In fact, I'm just going to do its half reaction right now, and I'm taking it straight out of the data book. Cr2O72 minus and 14H plus, and these are both aqueous. Reacts with 6 electrons to make 2 Cr3 plus and 7 waters. Okay, so there's our strongest oxidizing agent, half reaction. So what's the other player in this? Iron 2 plus. As a reducing agent, it has to lose electrons. So that means it has to make the more positive Fe3 plus and lose 1 electron. So when I go to balance this redox reaction, I've got 6 gained and 1 lost. So I need to times everything here by 6. Okay, now I can cancel out my electrons. 6 gained, 6 lost. And we have our overall redox reaction, 1 Cr2O72 minus reacts with 6 Fe2 plus to give 6 Fe3 plus, 2 Cr3 plus, and 7 waters. Okay, now this is really what we're after because there's our coefficients for a balanced redox reaction that we're going to need for the stoichiometry for our titration. Okay, so on our titration table, it says up here, step 1, find the average volumes. And these are the volumes of what? Titration of 10 mils of 0.05 iron 2 plus with, okay, so that means this is the volume in the burette. Because that's in the burette, that's what we're measuring the volume of. So subtract those and we get 11.5 mil, 10.6, 10.7, and 10.8. You know what's really sad? I was just thinking my Chem 20s won't get to do a single titration this year because all of that lab titration stuff is near the end of Chem 20. So next year in Chem 30, when we get to redox titration, they are not going to have a clue what these tables look like, how they work, what a burette is. Like, that's pretty lousy. Luckily for you guys, most of your stuff is kind of theoretical and based on knowledge that you already learned in Chem 20, so you're not missing too many labs. Okay, I'm getting distracted. So discard, always discard the first one if it's not within plus or minus 0.1. That's the ballpark or the estimate, so it's gone. So we have to take our average, 10.6 plus 10.7 plus 10.8 divided by 3, and we get an average volume of 10.7 mil. So that would be the volume average, and that is for our strong oxidizing agent. Okay, so I'm just going to write under here that we used 10.7 milliliters of this, and we were titrating with 10 milliliters of this, and it was 0.0500 moles per liter. Okay, we have everything we need to do our stoichiometry to figure out the concentration of dichromate. So in solution stoich, you always start with the one that you know its concentration and volume. So here we go. We've got 10 milliliters of Fe2 plus times its concentration. Okay, and that's going to give us the moles of Fe2 plus, and we're looking for the concentration of Cr2O72 minus. So the one we're looking for goes on top. 1 Cr2O72 minus reacts with 6 Fe2 plus. And now I can cancel out those Fe2 pluses. Okay, and now I can cancel out the liters off of there and leave the milli. So I've got millimoles of dichromate, and we want moles per liter. So my last thing to do is divide by the volume of dichromate. If you're going to screw these up, this is where you'll mess them up, is not using the correct volume. That's 10 mils of iron 2 plus. That goes with its concentration. And this is our dichromate, so it goes with the volume of dichromate. Those two have to go together, and these two have to go together. Weak students won't pay attention and they'll just interchange the milliliters and not understand which one goes where. Excuse me, so beware of that. Okay, so when we're all said and done, we will get moles per liter as our final unit. And when you punch it into your calculator, you should get 7.79 times 10 to the minus 3, or 0.00788 moles per liter. So that is the concentration of dichromate. Capital M, same as moles per liter. So you need to be able to do the half reactions. You have to calculate the average volume, and then you have to be able to do the stoich, solution stoich, to get the concentration. Okay, how are we doing? I was going to try and draw on my face, but it didn't work. Darn it. Oh well, you can do that at home if you like. I think that is it. So if you've already done the assignment and the quiz, you're done for today. Enjoy your Monday off. Those who haven't finished the assignment and the quiz, hopefully this video was helpful for you. And if you didn't get a chance, you should really check out Rosalind Fisher's video of what she was doing during the break to prevent herself from going crazy from boredom. She has an amazing 1-minute video. Just love, love, love it. It's got one of my favorite songs as her theme music, and it just shows off some real cool artistic talent. So nice work, Rosalind, and congratulations. You were the winner of the $20 gift card for best video. Take care, everybody. We'll see you tomorrow for first day of chapter 14. Okay? Bye.